All right. We trained a language-based artificial intelligence model to recommend a patient directly to a medical specialist and to identify their COVID-19 risk based on a description of the patient's condition. Let's start with the problem. In today's day and age, primary care doctors are overwhelmed with their amount of patients, which can lead to delayed treatment, according to a report from the Association of American Medical Colleges. When patients don't get the right care immediately, any disease or condition they have can worsen. In addition, they are at risk for misdiagnosis, overlooked symptoms, and COVID-19. The pandemic exposed our shortage of physicians, especially those in primary care. As you can see in this first chart, during a surge of COVID this year, many states had about 15 to 31% of hospitals reporting critical staffing shortages. This issue is not expected to get any better, as in the future, there's a projected shortage of 21,400 to 55,200 primary care physicians in the US. This further reinforces why a solution is necessary. Now, here are some definitions you'll need to know going forward. Specialized care is the field of doctors that address or specialize in a certain issue. The specialists we included in our algorithm are radiologist, general surgeon, urologist, orthopedist, neurologist, and gastroenterologist. Next, transcripts are text samples describing a patient's condition, and keywords are words relevant to the diagnosis of a patient. The figure on the right is an example of a patient transcript with the keywords in bold.
So what is our role here? Well, if you developed a health problem one day, what would you do? You'd probably schedule an appointment with your primary care doctor, but it could take weeks before you actually see them. And once they do look you over, they'll probably recommend you to a specialist, but getting up an appointment with that specialist could take weeks or even months. In the meantime, you've been dealing with your health problem every day. And if you happen to have a disease like cancer, it can pass into an untreatable stage. Additionally, we are in a pandemic, so we have to be careful about spreading COVID-19, especially in a doctor's office. That's where we come in. Our model attempts to recommend you directly to a specialist, so you don't have to worry about the wait time in scheduling an appointment with your primary care doctor. You type out a description of your ailments, get recommended to a specialist, and based on the symptoms you give our model, we will also tell you whether or not you are at risk for COVID-19. This allows you to get treatment in a timely manner and stay safe and protect others too. It is difficult, however, to create accurate models because multiple diseases have the same symptoms. For example, cancer and sinus infections can both cause fever, fatigue, and headache, but cancer is far more serious than the common cold. Patient transcripts can also be wordy and lengthy, which makes it difficult for the model to train and learn from. When the patient types out a description of their symptoms, our model will return two things. First, the specialist the patient should go to, and second, whether they potentially have COVID-19 or not.
The methods that we used to develop efficient models can be broken into 3 steps: data collection, data preprocessing, and model training. Using this approach, we developed 3 models: a transcript model, a keywords model, and a COVID-19 risk detector model. We used the transcript and the keywords model for specialty identification, which plays a significant role in our project.
To begin, we downloaded a dataset consisting of around 5,000 clinical transcripts and keywords from emptysamples.com. Since this dataset did not contain medical specialties, we sorted about 3,000 of these 5,000 transcripts into 20 different medical specialties. Examples of medical specialties include neurologist, orthopedist, gastroenterologist, etc. And because we also wanted to build a model to predict the COVID risk of a patient, we added a COVID risk column where we annotated the risk of a patient to be either yes or no based on their symptoms.
Since the dataset was highly imbalanced, meaning that there were many more data points for some medical specialties than others, we had to narrow our dataset down to the 6 most frequent medical specialties. Even then, the dataset was extremely imbalanced, so we used language translation as a means of data augmentation to alleviate this asymmetry. In order to have around 1,000 transcripts for all of the top 6 medical specialties, we translated the transcripts we had for these specialties into 3 randomly chosen languages: Portuguese, French, and simplified Chinese, and then back into English. Our main goal with this method was to balance our dataset by essentially finding synonyms for the words in the given transcripts. Then, we used programs from the Natural Language Toolkit library to extract keywords for the keywords model. The 2 programs we used were StopWords and POS Tagger. StopWords removed all of the common words that were not important in natural language processing, such as articles, prepositions, and pronouns. The POS Tagger tags each word in the transcript by part of speech, so the parts of speech that corresponded with keywords were kept, while unimportant parts of speech were removed.
For our model, we use the pre-trained Roberta model, which stands for a robustly optimized BERT pre-training approach. Roberta is a transformers model for pre-training natural language processing systems, which is what our model would be classified as we are working with textual data. We use the Roberta tokenizer, which replaces textual data with elements known as tokens, to tokenize our data because Roberta only recognizes data in certain forms. After running the model, we chose the number of epochs, which is the number of times that a model will work through the entire dataset that resulted in the highest accuracy. We also tweaked other hyperparameters, but eventually stuck with the default settings since they produced the best results. So we do have 2 different models, although their frameworks are extremely similar. And both models use Roberta and the Roberta tokenizer. And we ended up using 5 epochs for both models since this gave us the best results. However, the transcript model had no keyword extraction, meaning the entire clinical transcript was put into the model with no edits whatsoever, while the keyword model was fed only the keywords of each clinical transcript. As mentioned before, we used the Natural Language Toolkit library, abbreviated as NLTK, to extract relevant keywords from the clinical transcripts. After keyword extraction, we put these keywords into another Roberta model and set it to 5 epochs. Our third model determines the COVID risk of a patient based on their clinical transcript. Since the dataset for potentially positive COVID instances was, again, extremely imbalanced, we used language translation once more to augment the data so that we had around 1,500 positive cases and around 2,500 negative cases. After data augmentation, we put the new data into a Roberta model that was tweaked slightly from our previous Roberta models and changed the number of epochs to 4.
Our results show that the accuracy from the transcript and keyword models ranged around 78%, and the accuracy for our COVID-19 risk model was around 99%. On the table on the screen, you can see we showed both the accuracy and the average F1 score. The average F1 score is a specific kind of accuracy a metric used to determine the balance and ability of the model to predict well over different classes, rather than just being good over one class. The model had many different peculiarities. It has not been determined why the COVID-19 model accuracy was as high as 99%. This could be a consequence of overfitting, or the model could just be simply that good. Further research is required to determine the root cause.
Among the many things we learned through our project, a key takeaway is that in 78% of cases, the patient was directed to the correct specialized care doctor, which we believe shows potential in our project. That's why we are committed to continuing our work to gain further insights.
For now, we only predicted the 6 most frequently appearing specialties in our dataset. In a future model, we will try to identify more specialties and also focus on improving the patient experience. Additionally, our dataset mainly consisted of transcripts from the point of view of the doctor, and consisted of technical and specialized vocabulary rather than a symptom description. For this algorithm to work in a real-life scenario, a future project should utilize the dataset with text transcripts that come directly from patients. We would also like to package this technology into an app where patients can easily identify specialized care on their phone. Another possible task for the future is to improve the keyword extraction algorithm and possibly make it more efficient than the transcript model. There are many other keyword extraction algorithms that could work for this project, such as TextRank, TF-IDF, TopicRank, and KeyBERT. Some of these may have worked better than the NLTK POS tagger we used for our keyword extraction. We would also like to work more on hyperparameter tuning the Roberta model, which could increase accuracy.
Last but not the least, we'd like to thank Amisha, Michael, Arjun, and Saurabh for guiding us, and also show our appreciation to MP Samples for providing us with the datasets, which played a crucial role in our project. These are the references that we used for the project. Thank you for giving us the opportunity to present. We hope that you found it helpful.